So in this video we're going to define eigenvalues and eigenvectors. These are quantities which are defined for a given square matrix, and they're very closely related to these invariant directions that we discussed in the previous video. But rather than thinking in terms of the linear transformation, rather than thinking in terms of the function that's defined by multiplying by a matrix, we're just going to look at the matrix itself and try to understand this problem computationally. Okay, so what is an eigenvalue? So an eigenvalue is a number. Okay, it's a scalar. For some reason, so this is the Greek letter. This is a lambda. I'm not sure why lambda is the preferred notation to use here, but choose any book you want, you will find that lambda is the notation for an eigenvalue, right? You could call it any letter you want, but we'll succumb to inertia and we'll stick with lambda. You know, everyone else is doing it, so we might as well follow suit. Right? We've given in to peer pressure. Now, what does it mean for a number to be an eigenvalue of a matrix? So we say that lambda is an eigenvalue if you can find a vector x, a non-zero vector. So this is kind of your, in the context of the last video, this is giving you this invariant direction, right? So x is, we're not interested in the magnitude. We'll see soon that the magnitude of this vector is irrelevant. What matters is the direction, okay? And so we're looking for this direction which is preserved, so that when I do a times x, I get a result which is parallel to the original vector, right? So this is saying that you know, a times x is parallel to x, right? So these are parallel vectors, okay? All right. So that's the idea. So we're looking for vectors that when we multiply by a end up parallel to themselves, and of course they're parallel, but they might be stretched or shrunk or flipped around. So we're looking for, well, what is that factor? Okay, so here's an example. All right, 2 by 2 matrix A. We've got the entries, and we can give an example of a couple of eigenvalues and corresponding eigenvectors, right? Now, don't worry, we will tell you how we came up with these pretty soon, right? Here we're just showing that it works. You might wonder where the hell did these come from? Don't worry, we'll tell you. Okay, so if I take the vector 4, 1, I multiply on the left by a, right? So 2 times 4 is 8 minus 4. 8 minus 4 gives me 4. Minus 1 times 4 plus 5, I get 1, right? So I get back the same thing, you know. So if this is x, right? In this case, a times x equals x, right? So that means x, which is you know 1 times x. So lambda equals 1 is an eigenvalue, and then for this other vector here, here's a times another vector. So this is my, or maybe call this one x1, right? Here's my x2. So if I do a times x2, I get this guy, and we notice that it is 6 times x2, right? So the result is still parallel to what we put in, but this time there's a scale factor of 6. So that's my other eigenvalue, lambda equals 6. And we have the eigenvectors that go along with them, 4, 1, and 1 minus 1. So 4, 1 is an eigenvector corresponding to lambda equals 1. 1 minus 1 is an eigenvector corresponding to lambda equals 6. Now there are some obvious questions you can ask at this stage. We found 2 eigenvalues. Could there be others? Are these the only ones? Maybe there are more. If this is all we can find, if it's only these 2 eigenvalues, what about the eigenvectors? The 2 eigenvectors we found, you know, are those the only ones? You know, could I find other vectors that correspond to lambda equals 1? Could I find other eigenvectors for lambda equals 6? You know, or do the 2 I have, do they kind of describe the whole situation? Turns out that what we have here is you know, up to scalar multiples of these vectors. The information we have on this slide is everything, but to see that is going to take a little bit of work. Okay, so the starting point is the following theorem. All right, suppose you have an eigenvector for a matrix with a corresponding eigenvalue of lambda, right? Now, if I take that vector and I multiply by a scalar, I get another eigenvector, right? So that's, as I was saying, once you have one eigenvector, any scalar multiple is another eigenvector, right? So I could take, say, 8, 4, I could take 2, minus 2, or maybe I want to swap the signs here and I do minus 1, plus 1. So once I've got one eigenvector, any scalar multiple of that eigenvector will still be an eigenvector for that same eigenvalue. Okay, so the proof is simple. So we start out by assuming that we have an eigenvector with a corresponding eigenvalue of lambda. So our hypothesis here is that a times x is equal to lambda times x, where x is not the zero vector and lambda is any scalar. Okay, so that's our assumption. We've got one eigenvector with eigenvalue lambda, and we want to show that any scalar multiple of this guy is also an eigenvector. So, well, that's simple enough. How do we show that k times x is an eigenvector? Well, we got to multiply by a and get lambda times what we started with. So how do we do that? Well, one of the things we know is that if you've got a scalar inside of a matrix product, you can bring it out. So this is k times ax. What do we know about a times x? Sitting right here in front of us. A times x is lambda times x. Okay? And one of our properties says that if I got a scalar times a scalar, I can put those together. And of course the order in which I multiply these scalars doesn't matter, so I can write this as lambda times kx. And then we're done, right? Because what I've shown is that if y equals k times x, then ay equals lambda y, and that tells me that this y is also an eigenvector. Okay, and so because of that, that's the sense in which we can talk about, invariant directions for a matrix transformation, right? If I have a vector x that works, then any scalar multiple also works. So anything in the span of x also works, right? And so if I take any vector along this line and I multiply by the matrix A, I get another vector that lies along the same line. This is what we're doing here. Okay. Okay. So we have certain directions that are preserved when we multiply by these matrices. Now, how do we find them? How do we find the eigenvalues and the eigenvectors? We need one more theorem. So how do I find these eigenvalues, right? Well, by definition, if lambda is an eigenvalue, that means that I can satisfy this equation here where x is not equal to 0, okay? Well, so what we do is we say, okay, suppose we satisfy that equation. So suppose lambda is an eigenvalue. Okay. Then a times x equals lambda times x for some vector x, which is not the 0 vector. Now let me rearrange this equation. Let me write this as so 0, it would be equal to a times x minus lambda times x, okay? And I want to kind of factor that x out, but the problem is that I can't write this. So a minus lambda times x, right? Doesn't make any sense because a is a matrix, lambda is a scalar. I can't subtract a number from a matrix, right? So the key to getting around this problem is to realize, well, lambda times x, and we mentioned this in the last video in our example with multiplication operators, this is the same thing as doing lambda times the identity times x, right? Because multiplying x by the identity doesn't change anything. Okay? So I can put the identity in there, and now I've got a difference of two n by n matrices, right? This will be the n by n identity matrix. And that makes sense. Now I've subtracted matrices, okay? But now look at what I have. What do I have? This is a homogeneous system. And x is not the zero vector. So x is a non-trivial solution to a homogeneous system. So think about our properties of matrices. What do we know? Well, one thing we know is that if I have a non-zero solution to the homogeneous system, then this matrix cannot be invertible, right? Our invertible matrix theorem tells us that the only way we can have non-zero solutions to this homogeneous system is if this matrix does not have an inverse, right? And one of the other things we know is that the only way a matrix fails to be invertible is if its determinant is 0. So the determinant must be equal to 0. So what we'll see in the next video is that this equation, this consequence of this result here, this is an equation which can be solved for lambda. So what we do, the way we figure out the eigenvalues, is we figure out the values of lambda that make that determinant equal to 0, and that's going to give us our eigenvalues.